right, so I'll be presenting joint work on algorithm configuration for constraint solvers. And so this is joint work with a lot of people from our lab, of which Senne and Lize are available in our audience as well. And so my name is Ignace Bleukx. And so if you have any questions, please feel free to ask them at the end of the presentation. So I'll start with a quick overview of what my presentation will look like, and then I'll just dive right into the motivation of the problem. So in our lab, we use the CPAIOR library. So it's quite modern Python-based constraint library, and so we can use it for modeling and constraint and solving constraint problems. And so we can, of course, use it to model a variety of problems like routing, scheduling, and packing, of which you're all experts on, of course. And so in a lot of applications that we do in our lab, we actually repeatedly solve very similar problems. And so on the one hand, research-wise, this is, for example, decision-focused learning or explanation generation, but also in the real world, where we have applications like daily scheduling of machines and daily routing planning. Those problems are very similar and have to be solved multiple times. And so, of course, everyone wants his models to be solved fast. And so how can we do this? Well, we have some very nice state-of-the-art constraint solvers. And many of those actually expose a lot of parameters to be modified in their API. So, for example, settings for heuristics or pre-solving parameters, of which I'm sure you know the exact details much better than I do. And so if you assume that the similar hyperparameter values work well across different problem instances, then we can actually just tune our constraint solver and find the correct hyperparameter settings and just use that same configuration on other instances as well and speed up those solving times as well. And so this is very easy to do in CPAIOR as well. So this is a small example of how to set the parameters for the CP set solver of OR tools. But so now the question remains, how can we actually find that the optimal hyperparameter configuration for our problem? Well, a naive solution would be to just search throughout the entire grid of the hyperparameter space. So we just choose one random configuration. We evaluate the runtime of the solver on it, and then we are done if we have done the entire grid. Of course, if this was a solution, it wouldn't be a very nice paper, and so we want to improve this strategy a little bit. And actually, we do this on two fronts. So on the one hand, we want to improve the search. So we want to have an informed decision, like when we pick another configuration to test, will this improve the runtime or not? And then on the other hand, when we do make a bad decision, we want to abort solving the problem with that configuration very early on. And so these are challenges that are tackled a lot in algorithm configuration. So this field in generally just finds good parameters for some target algorithm, and is very often used for classifiers or neural networks. And in that setting, the measure that we try to optimize is the accuracy on some test sets of instances. In the case of our constraint solvers, we know that the solution that is returned is always of the same quality, right? It's a feasible solution or an optimal solution, depending on the setting. And so the measure that we actually try to optimize is just the runtime of the solver. And so how can we exploit this? Well, just to find and so we want to exploit this idea to guide the search. And algorithm configuration has some very nice framework called the SMBO framework, or sequential model-based optimization. And so what we do in that case is just to replace the target algorithm by some surrogate model that's very easy to evaluate. And then we use that surrogate model to compute a score for a certain hyperparameter configuration. And then, of course, we can select our next best configuration based on that. And so for the case of optimizing the runtime, it would look something like this. So our surrogate model in the middle, takes as input parameter configuration X, and then it outputs the approximate runtime that we might expect from that configuration. All right, great. So we can guide a search. Algorithm configuration has solved this already for us. So let's go to the next problem or possible improvement. So we want to discard bad configurations early on. And in the field of algorithm configuration, again, we call this adaptive capping. So what this means is that at some point in our search, we have some up until then optimal configuration, and it has some runtime. And so actually we can just abort any solve call that exceeds that time, right? So this speeds up the search massively, even when we search throughout the whole grid. Because if you find a very good runtime at the start of the search, we can very quickly time out more configurations later in the search. And so the evolution of the runtime would look something like that, for example, when searching throughout the whole grid. Unfortunately, we don't know the real runtime of the timed out configurations. And we'll get into why that is actually a problem. So we want to guide the search and discard configurations, as these are very nice properties. However, we cannot have both, because the surrogate model in the SMBO framework actually requires the uncapped runtime, the real runtime of that configuration to update its parameters or whatever it is modeled as. Or can we, right? In our work, what we propose to do is, instead of directly modeling the runtime of a configuration using some surrogate model, we actually model the probability that the configuration will improve the current best runtime, so that it will be better than the runtime that we have found up until now. And this fits very nice in the SMBO framework. So we just have to modify two lines. So when evaluating F, so evaluating our solver, we just kept the runtime, that's the up until then best runtime, and we update our surrogate model, the probability model, using that kept runtime. All right, so now the question remains, how can we actually model this probability? So the intuition that we had is, if we actually want to use configuration or to test configurations that might be promising, and promising in this case means we want to use hyperparameters that have actually already improved the runtime before. And so we have two ways to do that. One is distance-based, and the second one is counting-based. And I'll start with the first one. So as a first example, or first surrogate, sorry, we use the Hamming distance to the current best solver, to the current best configuration. And of course, our score is just the Hamming distance across the hyperparameters values of a certain configuration. And then our model just consists of the optimal configuration up until then. And as a small example, let's say we have the following hyperparameter search space with 3 parameters. The first one taking values A, B, and C, the second one I and J, and the third one are S and T. And so at some point in the search, the current best configuration we found is BIR. And then we can just compute the Hamming distance to that current best optimal for every configuration or every hyperparameter configuration that's still left in our search space that we have not tested yet. And so in this case, we would pick AIR as it has the lowest Hamming distance to the current best configuration. So that's one way to do it. Another way to do it is to use a counting-based surrogate model. So the intuition behind this model is to count the number of times that a certain value of a parameter has improved the runtime previously in the search. And so this actually just maps on the categorical distribution or the Dirichlet-based distribution. And so what we will do is we just count the amount of times that a value for a hyperparameter has improved the runtime, and we decompose the entire configuration to every hyperparameter. And this assumes that the parameters are independent, which is of course quite a strong assumption, but we'll make it work for now. right? And so going back, so this is what the surrogate model and the scoring function would look like. So we just take the product of every probability that a value will improve the runtime for every hyperparameter in the configuration. And then we can very easily update our model based on where it improved the runtime or not. And so going back to our example of before, so we, in this case, at some point in the search, we have seen 5 configurations that improve the runtime with value A for parameter 1. We have seen 1 configuration with value B for parameter 1. And of course, this holds true for the other parameters as well. And so then we can very simply compute the combined probability that the entire configuration will improve the runtime based on those counts, right? And so in this case, we would take the configuration AIT as a next promising candidate and evaluate the runtime. All right, and then we can actually also combine those two, as we saw in the example of the Hamming distance. A lot of configurations will be at the same distance of the optimal configuration in the start of the search. And so we actually also use the Dirichlet-based surrogate model to use as a tiebreaker in the Hamming case. All right, so how do we evaluate this ID? So we introduce the relative improvement of the timeout or of the runtime, where 0 denotes the runtime of the default configuration, so just the configuration that the solver comes with, and 1 denotes the runtime of the best configuration. And then we can very easily average results over a lot of different models, as it doesn't take into account the absolute runtime of that model. And we did some experiments with this, and unfortunately what we found is that in the first few iterations, the surrogate models don't really help us, right? So the random uniform search that we took as a baseline was actually better in the first few iterations. Later on, it does improve a little bit using those surrogate models that we introduced, but not by a lot, unfortunately. So it only benefits us after a few iterations. So relating to our previous thought that we had, can we guide or jumpstart the search from the very first evaluation, right? And so we can actually compute priors for this. We have our Dirichlet or categorical distributions with those nice pseudo counts. Can we, instead of initializing those uniformly, can we initialize them based on the search that we have done somewhere in the past? And the way that we do this is just to take all of the configurations that are in the threshold or some threshold of optimality in some training set, and then we rescale the counts for every value of the hyperparameters to work in that Dirichlet distribution. And apparently this worked very well. So when we use those pseudo counts to initialize the distributions, the search gets guided from the very first iteration, and we actually see very good configurations very early on in the search. And so these are the same results in tabular form. And so actually the surrogate model that uses Hamming distance and informed Dirichlet prior as a tiebreaker was the best in this case. And so just to conclude, of course, hyperparameters are very useful for setting or improving the runtime of your solver. And so when searching throughout the whole grid, the order that we pick configurations to actually check or to evaluate matters when using adaptive capping. And so our simplistic surrogate models didn't really do much in terms of improving in the first iterations, but it did when we introduced prior knowledge to jumpstart the search. And so for future work, we have some ideas for this. So maybe we can evaluate the solver simultaneously on different instances or multiple instances of the same problem type. So for example, different knapsack problems, or configuration problems. We also really want to try our approaches that we now had on larger problems, as we've now mainly focused on smaller problems. And we also, of course, want to do this for other solvers instead of only the CP set solver of OR tools. And so with that, I happily conclude with answering any of your questions that you might have. Yes.
So there is some recent work from Kevin Layton-Brown and Robert Bleinberg, etc., with some theory on optimal algorithm configuration with capping. Okay. So is there any connection? Is there any relationship?
I'm not really familiar with the road, to be honest. Do they also use SMBO framework, or?
I have to check. There might be some version.
Okay, that would be interesting, actually. Yes.
Thanks.
Might be in the same direction. Your notion of counting how many times upper parameter setting improved reminded me of Shapley values. Have you? And then there is also SHAP as a formulation of this for upper parameter tuning. Have you looked into this?
No, not really, to be honest.
It might work really well with your prior design. Maybe the Shapley values could, they basically take the average marginal added utility from the setting. It might be interesting to shape your price.
Yeah, we mainly evaluated two paramills. That's not really designed for solvers, but it does also support adaptive capping, and so that's we mainly used methods like that to compare to. But I'm not really aware of that work, to be honest.
I was thinking that two other things you could look at in optimization problems is look at intermediate solutions and how good they are as a metric, or maybe look at the failures we can get this out of your solver. That might give extra information you can get would be useful.
Yeah, sure. But I think it does matter on the problem that you're trying to solve as well. Because when I don't know you're using optimization problem, maybe the most of the time will be improving optimality at the end, for example. And then I'm not sure that intermediate solutions might really work. But using more information will certainly help the search in that.
Yeah, it's much less direct. I'm sure there's problems where, okay, well, we get a really good intermediate solution at the start, but then optimality is actually much further away than like the multi-server. But if you map this out, then maybe for certain instances, and you know that a good first intermediate solution is also proxy for an eventual fast optimal solution. And maybe in those cases, that apply.
Yes, indeed, might be very interesting indeed.
Thanks.
So I suppose to generate the data in your prediction model, you have the configuration, but also you should have a representation of the instances.
Sorry, can you repeat your question?
So how did you generate the data?
We used existing models of Hakan Kjellestad. I don't know if you know him. So he modeled like a whole library of models in constraints, or like in CPMPI as well. And we just used those models to get the results of it.
But the input output, you have in the input you have the configuration.
Yes.
And the output you have a prediction of the runtime.
In the traditional case, we do, yes, but in this case, we just model probability, and so the input configuration is just any configuration in the whole hyperparameter space. But it's just we evaluate every single configuration, so we don't have to sample anything. I'm not sure I really get your question, to be honest.
Yep, because it depends heavily on the instance you try to solve. If you have two different instances and you try with the same configuration, you can end up with a very different runtime.
Yeah, but so we're not estimating runtime. We're estimating probability that it will improve on the current best instance.
The improvement.
Yes. No. Just whether it's going to be better. So it's a classification. The model is it's a probability. Is it going to be better? Yes or no? That's easier to fit, we think, than regression.
Just to follow up, but the current best is a moving target.
It is, yes. And that's why we do the Bayesian updates. It's still in the Bayesian and sequential model based.
But you're counting how many times you improved it, and like improving early on when your current best is low, like why does it matter?
So it matters. So it matters so much that we even add a Hamming distance to say closer to the current best one.
No. In a sense, early on in the search, when your current best solution is a low baseline, improving like what flipping a parameter and improving on that low current best baseline is an easy target. And then a particular parameter value, in a sense, contributing to you winning that low baseline is not really an indicative thing of it being a good value later on when you have a stronger baseline as you improve your current best.
Well, and that's why we do the sequential updates. So it's best, it's good, and then okay, and then it's good again, okay, and then no, and then it becomes less important than the other ones. Increasing importance.
So you're forgetting some of those early
It's
on
automatic
success.
Bayesian updates. Yes, but if it's negative, then we subtract.
Yeah, and there's also like the possibility of weighting it more explicitly. You could like say that you could make it explicit that you give a low weight to old information, but we haven't really looked into
No, we haven't looked into that now.
But at least there's some forgetting already just built in.
Yes.
Second question.
Oh yeah.
So have you compared yourself or your network also against like the classics, like an F-race, integrated F-race or SMAC?
We didn't really because they don't support adaptive capping. So
As far as I know, SMAC does that.
do they?
Well, we actually did compare, but it was incomparable because without the adaptive capping, it was so much slower. So maybe we missed that, but it uses the regression model. So if you adaptively cap, then you cannot update your regression model because you don't know what the full runtime was. So maybe we missed it, but yeah.
So this is just, I mean, I can't point you to the place in the code, but as far as I know, SMAC does that, for example.
Okay.
But of course, it depends on the scenario that you give to SMAC, depending on whether you want quality or runtime, I believe.
All right, we'll have another look.
All right. Well, thank you very much.